Question number 5. Okay, let's see. We have a function that looks, at least my version, looks like that. We have another line called x equals 11, and it's going to be rotated about the x-axis. Right, I'm going to just go in and mute everybody for background sounds. There we go. So you hit the space bar now if you need to talk to me. Okay, this is basically the question. Does that look right? Whoever, was it you, Ripken, that asked?
Yeah, it looks right.
Okay, it's right there. Right, so we're going to rotate this about the x-axis. So the first thing I'm going to do is draw a sketch of this bit, this region, so I get an idea of what's going on. And since I know it's being rotated about the x-axis, will my formula that I'm about to use, will it use these x's or will it be using y's? Because that's a big decision. X's or y's when you rotate it. Okay, so we know we're going to do the integral from y equals c to d, 2 pi, a thing called the radius, multiplied by a thing called the height, dy. So that's the very generic formula that we're going to use. So I got to get this guy into my calculator, well, not my calculator, into Desmos. So let me go over to Desmos for a second and see if we can see what this thing looks like. Right, so I have x equals 2 plus, in brackets, y, subtract 5, close brackets, squared. So when I hit thingy above it, it does it. Right, so there's the guy, right? The red curve. Now it has another line that went said x equals 11, so I'm going to put that fella in. And between them, I should have a region. Should be blue. Oh, God, it's in front of me. There. Do you see that the region I want is this red bit, this blue bit? So everything here on the left-hand side. So I'm doing a very bad sketch of what I can see. Oh God, it's a horrible sketch, but who cares? Right, what do I need to know here? I need, this is 11, I guess. I need to know this number where the blue line and the red line meet, because that's the intersection points. Would you agree that the top value where the line and the curve meet is 8 and the bottom value it's 2? And that should be everything. So I can now return back to my piece of paper and show you what I've got. Right, that's my bad version of what it looked like. Vertical line, right? Curve, shaded bit. The 2 was here, the 8 was here, right? Everything that we need is in the picture. So the volume is going to be the integral from 2 to y equals 8. Stick the 2 pi out the side. And I've 2 guys to get, and this is the kind of the end of the story. If you randomly draw a line, a green rectangle, parallel to the axis of rotation, this guy here, he is y, and this guy here is x, right? So the fellow we call the radius, the fellow we call the radius is the distance from the rectangle to the axis of rotation. So that distance here to here, I'll do it in red. That distance here to here is my radius. Isn't the radius just y? So the radius is y. Now, the thing that we call the height is the distance from here to here, right? And I'm looking at that distance and I'm saying that far away distance is 11. This distance is x. So I guess the height is 11 take away x. We don't want x. We want things in terms of y. So I'm going to use the fact that since x is on the curve, x is also equal to this guy. So I'm now going to take away all of that. Now that in itself is a little side issue, because you know that you can make that look a lot prettier, right? So all I'm going to do is subtract 2, subtract that. I guess I've written it, so I'll keep it. Foil that out, you get a y squared, then you subtract it. You get a negative 10y, but then you subtract it. And you get a positive 25, but then you subtract it. So what you get is minus 16, a minus y squared, and a plus 10y. Let's see what that looks like. Yeah, it does. So in here, I'm going to go negative 16, negative y squared, plus 10y dy. Well, what am I going to do next? Because this question's pretty close to being finished.
Distribute the y.
Okay, so the volume is going to be the integral from 2 to 8 of negative 16y, negative y cubed, plus 10y squared dy. And at that point, isn't it just a very, very ugly power rule with lots of numbers that you chuck in, and provided I didn't do some silly mistake where a plus should be a minus, the process is correct, right? So you should be able to follow it through. Okay, do we have any other questions from 6.3 that you'd like me to go over before we move on?
I actually have like a question in general.
Sure.
When we're trying to find, let's say in this instance, the height,
Mm-hmm.
there's been some questions where we would have 11 take away x, and then other questions would be x take away 11.
Right. And
How
so
would
when is it one and when is it the other?
Yeah.
Right. Well, context is essentially what you have here. So in this case here, I want to find the length of that guy, right? So the furthest to the right goes first. So in this case, it's the 11. Take away the other guy. Now, if you imagine a story where the line was here, say the curve was there, and my rectangle was going this way, wouldn't the curve be to the right and the straight line would be to the left? So in this case, you would get x take away 11, whereas in this case, there we go. In this second situation, the guy to the right is 11 and the curve is x. So it depends on the orientation, where the vertical line is compared to where the curve is. Now, if you do it the other way, do you know the ones that go like this and the line going like that? In those cases, isn't the rectangle going this way? So in those cases, top guy take away bottom. And if the straight line is there, but the thing is there, which can happen, can you see that you'd get top guy would be the straight line and bottom would be the curve? So orientation is the key to who goes first and who goes second. Does that make sense? Now, if by chance that's the only thing you do wrong, that you say 11 take away whatever the function is x, right? Or x take away 11, you do it the wrong way. Do you know that if you do everything else correct, you will get the right answer, it'll just be negative. So if you get negative 22 pi, that's a sign that you did left to right instead of right to left. So you can actually tell when you've done it the wrong way around as well. Does that make sense? Okay. You're smiling like you got a negative answer once, then now you know why.
Many times, many times.
That you just got the negative version of what you wanted.
Yeah,
I
and
wa-
then I was so mad. I was so mad. I just restarted the whole entire thing. I didn't realize that I just had to take away the negative sign.
Hey, we learn something new every day. Now, the cool thing about that is you'll not make that mistake again, right? So you've learned, and that's it. We move on. Okay, last chance. Any more questions about this? If not, we can start getting a move on to our next section, which you'll be glad to hear is a lot easier. Okay, looks good. Give me a few seconds to just set myself up, and then we will be ready to do it. Doing things just a little bit out of order, but just a little bit. The next section I'm going to do is 6.5, which is the average value of a function. And the reason I kind of want to do that first is so that I know exactly how much time we've got left for the final section in chapter 6. So it just makes it easier for me and hopefully for you if our time is kind of organized in that fashion. So where shall I go? Well, let's tell you about section 6.5. Its heading is average value of a function. Fn is short for function. Okay, imagine that you had a function that started at x equals a and finishes at x equals b, and it went there and it's the usual. Now, when we talk about what the average value of a function is, it has the same meaning that average means. And the difference with this is that you have to find the average of an infinite number of y values. So can you imagine that x was time and the vertical axis was temperature? What you're looking at is the temperature change throughout the day. And if someone said, well, what was the average temperature during that day? Well, I guess, couldn't you measure the temperature once an hour for the whole 24 hours? That'd be 24 temperatures. Divide that by 24, and that would be your average temperature. Now, if you wanted to be a little bit more accurate, couldn't you measure the temperature every minute and average out a huge number? You could keep going, couldn't you do it every second, every microsecond? Well, imagine we wanted to find the average value of a function, because that's essentially what we want to do. We want to find out what's the average height of the function. And the formula for it is very simple. The average value of a function is 1 over b minus a, the integral from a to b of f of x dx. So we don't have any radii and height to calculate. In fact, if we know how to integrate, can't we do these questions without any real problem? There's nothing significantly going to change in any of the question examples that I'm about to do. So when you're finished, that number is, I don't know, 22 or something. Can you imagine that there's a value somewhere about here? And that's the average height, the average value of the function. Okay, let's see what it's like. Suppose I give you a polynomial like x squared plus 1, and I want to know its average value from 0 to 2. Then the average value of a function, and let's get some notation. Sometimes you'll see it in textbooks written like this. Sounds like I'm trying to write the word favorite, but it's f subscript average. That's essentially what it's saying. It's another way of saying the average value of the function. It's going to be 1 over b minus a, the integral from a to b of our function dx. Well, if you call that a and you call that b, it's 1 over 2 take away nothing, nothing to 2 of x cubed plus 1 dx. Essentially, isn't it just integrate a function? And this, what do you think this 1 over b minus a is all about? I mean, if I took that out, haven't I just found the entire area under the curve? So what do you think the b minus a, which is essentially dividing it by b minus a, is all about? It's a bit like dividing by how many things there are. You know, like when you do an average, it adds up to 40, but you divide by 10 because there's 10 numbers. It's kind of connected to that. So in this case, it's 1/2 power rho (2, 4, 8, 6, 4, 6). 1/2 of 6 take away nothing. 1/2 is 6. The average value of that function is 3. So if I sketched f of x equals x cubed plus 1, and I did it from 0 to 2, the average value of this function is about here. So we know on average its height's about 3. If this represented some kind of temperature, the average temperature during the day would be 3. So let me do one. Suppose the average temperature, not the average temperature, but the instantaneous temperature was given by t squared plus e to the t. And I would like to know the average temperature in a 24-hour period. And this particular place isn't on the Earth. It's in Mercury or some place that is extremely hot. So here goes. The average value is 24 take away 0, the integral from 0 to 24 of t squared plus e to the t dt. Would you agree that the formula is pretty simple? It's really just an integral with a little fraction stuck at the front. In this case, the fraction is 1/24. This fella is a little bit messy, 1 over t cubed plus e to the t, evaluated at 0 and at 24, which is why I got my handy calculator handy. Yeah, because we're going to do a ridiculously big number in a minute. 1/3 times 24 cubed. So there's 24 cubed. And I'm going to divide that by 3. And I get 4608 plus e to the 24. And that's your answer. I do not want decimals, which means e to the 24 is just going to stay as e to the 24. But trust me, that is like melting lead kind of temperature, which actually I think is true. Yes.
Isn't e to the 0, 1? So
oh, e to 0, 1. I forgot. There's going to be a -1 to that. There's going to be a takeaway 0 plus 1. So it's going to be 1/24, 4608 plus e to the 24, take away 1. Although in the big scheme of things, that number's so huge, you think takeaway one's going to make much difference? Probably not. Are we good? So I've done an average value with a polynomial. I've done an average value with an exponential. Let's do an average value with something trig-like in it. So who's got trig? Yeah, that's it. The function's going to be sin x. We're going to do it from negative pi upon 4 to positive pi upon 4. And we're going to find its average. Let's use that notation. It's going to be 1 over pi upon 4, take away negative pi upon 4. The integral from negative pi upon 4 to pi upon 4 sin x dx. Now I'm about to do this calculation, but I already know the answer. Does anybody know what the answer is going to be before I even do it?
0?
Yeah. And we'll come to why that's the case in a few moments. So that guy plus that guy gets you half pi. This fellow gets you as an antiderivative negative cosine x evaluated at this fella and at this fella. Do you know 1 over pi over 2 is the same thing as 2 over pi? Okay. Negative the cosine of pi upon 4. Take away negative is add the cosine of negative pi upon 4. That guy is negative root 2 over 2. This guy is positive root 2 over 2. That's where the 0 came from. Now, how did I know, and at least one other person also knew, why the answer to this thing is going to have an average value of 0? Well, let's sketch the sine function. Can you see it's an odd function? Half of it is below the curve, half of it is above the x-axis. Aren't they symmetrical? Won't that bit cancel this bit? The area is going to be 0. Does it make sense then that the average value would also be in the middle, which is 0? And that's why we got what we got. Now, compared to the last 2 days, I hope you are saying, I like this. This is straightforward. I don't have any real major decisions to make. In fact, I probably don't even need to draw the picture because won't the formula take care of it for me? Would that be a fair idea of what most of you hopefully are thinking? This is not that difficult to do, at least compared to what we've done. So let's try and keep it that way. Here's a new function. Oh dear, this is not easy. Okay, there we go. I'm just making a question up that hopefully comes out right, relatively nice numbers. An average value of this function. By the way, there's no reason that needs to be 0. Would you agree it could be any number? I'll just pick 0 because it's easy to do. Okay, we got a problem. That's the problem. Look at that integration. I need a technique. How am I going to find this fella?
U sub.
Agreed. Who's the U sub? And U subs don't go away, right? You're going to be doing U subs to week 11, right? Trust me. They're going to disappear, and then, you know, the next day you do 3 of them, right? Whatever. I need a U sub. Who shall I pick?
16 plus x squared.
Right. Remember the rule, the ugly guy inside the square root is a good candidate for the U sub? That's this fella here then. So you differentiate with respect to x. You do the crossover. And then you isolate the dx. Hopefully, the U sub method is becoming second nature to you. Now let's see what we get then. Well, we're going to get the integral 4x over the square root of u times 1 over 2x du. We're going to get a little bit of cancelling, and we're having that guy. Okay, we need to deal with this situation. Is there anything I can do to help solve the antiderivative of this?
Could you make it into -1/2 to the power of -1/2?
Exactly, yes, I would. Does that seem reasonable? We've done things like that before. Now, isn't this a power rule? Power rules work with fractions. Add 1 to the power, you get a half. Divide by the new power is basically doubling things, so that's why you get a 4. And then convert it into its original form, and then return back to the x's so that we can do the limits of integration on it. Are we good? Add 1 to the power, divide by the new power. That becomes a square root, which in turn becomes this. And this gets evaluated at 0 and 3, because it is x's that we're using here, not u's. It's not u equals 0 to u equals 3. It's x equals 0 to x equals 3. So let's see what that gets me. If you plug in 3, you get 9. 16 add 9 is 25. Square root of 25 is 5. 4 lots of 5 get you 20. You plug in 0, you get 16. Square root of 16 is 4. 4 4s are 16. So you get take away 16. And the final answer, the average value of this particular function is 4/3. So if you sketched it, it might start low and it might finish high, but its average height is going to be about 4/3 of the x-axis, about 4/3 high. Any issues with that, or are we okay?
I'm kind of confused with the part where it went from to. Oh wait, no, I see it. No, I'm fine.
Yeah, we're good. Okay. And sometimes you just go back and watch, skip to the bit that's important, and then you watch this video, and then you say, okay, I'll just pause it for a second and see what he's doing here. Okay, now I got it. And that's how you learn. So I would learn it. Let's see what else we have. Okay, since we're on interesting integration issues, here's our next one. I want to find the average value of e to the sine x times cosine of x, and I want to do it from 0 to pi upon 2. So the average is 1 over pi upon 2 take away 0. The integral from 0 to pi upon 2 of this guy. Okay, pi upon 2 on the bottom is the same as 2 over pi. That wasn't much of an issue. Now, do you recognize that this is also a U sub? Agreed? Give me a U sub to use.
Sin
Sin
x.
x.
Agreed? Wouldn't this qualify under the e to the ugly guy rule? Use the ugly guy. So when you differentiate with respect to x, you get cosine. When you do the crossover, and then finally isolate. Good practice, isn't this? It's good practice at U subs. Now, it's going to be the integral of e to the power of u cosine x times 1 over cosine x du. And sometimes it's just so elegant, it's kind of, is that not pretty? It just is so nice looking. Yuck, ugly, yeah. Elegant. Well, we're just going through the usual thing. Antiderivative. If e to the u is still e to the u. Convert back to the original so that we can evaluate it at 0 and pi upon 2. So what we got? We have e to the sine of pi upon 2. Take away e to the sine of 0. What is the sine of pi upon 2? Because it is a number.
1.
So isn't that basically e to the 1, which we typically just call e? And sine of 0 is 0, and isn't e to the 0 the number 1? So we take away 1, and we're finished. No decimals. Exact value, we're done. You comfortable with that question? Anything in it that you want me to explain a bit better? Okay. Do a trig one. Change the letter of the alphabet. Here's our function, p of x. It's obviously it's a trig function with sines and cosines in it. We're going to find its average value. Did you hear the Invisible Man and Superwoman had a baby? No. The baby was nothing to look at. I'm going to let that one sink in for a minute. Come on. Ripken, you're good. You like that one? Was it that bad it was good?
Yeah, it was that bad. That was good.
Douglas, I'm not so sure you appreciated that bad joke. Okay. Okay, let's continue then. Whoa. USUB. Sneaky one, but we have seen ones like this before. This is how experience, that's basically doing stuff, homework, whatever, helps in the future. You've at least seen one or two just like this, and it was a USUB every time, okay? And now you have to try and remember which one did you pick for the USUB, because one of them works and the other's no good to you. And of course you have a 50-50 bet if you're a gambler, but if you've used your experience, it will tell you the right one to use. So which is the right USUB?
Cosine.
Do you want to tell everybody, that's the correct answer by the way, why you chose that one? What was it made you think cosine?
Well, when you take the derivative and then move it, it'll be 1 over sine, or 1 over negative sine, and then it'll cancel with the sine.
Yeah, pretty much. So if you differentiate a cosine, now do you notice that I'm differentiating? You've got to have your differentiation hat on at this stage, right? Later on we have an integration thing, but right now we have this guy. Just like you said, we have that. So our thing's going to become 3 times u cubed, a sine x, a negative 1 over sine x du. And it's going to cancel with a little negative in front of it. We got that. Would you agree it's just a power rule? So I'll add 1 to the power and divide by the new power. So that's where the negative 3/4 came from. I'll return the u to a cosine, so u to the 4 becomes cosine x to the 4. And now I can evaluate it at the 0 and pi. Right, cosine of pi. Isn't the cosine of pi negative 1?
Yeah.
Great. So negative 1 to the 4, isn't that just 1 again? So that's where the 1 came from. Take away a negative is adding. So it's going to be add 3/4. Isn't the cosine of 0 1? So cosine 4 is 1, so you're going to add that guy. Oh. The average value is 0. Well, the only way that could happen is that if we looked at this function from 0 to pi, shouldn't half of it be above the x-axis and the same amount of it should be below the x-axis, and so that they cancel each other out and you've got basically the x-axis or 0 height as the middle, right, the average. Great?
Professor.
Yes.
So like we're calculating the average volume basically?
Not volume, just average height of the function. So there's no volume involved.
So like what is height exactly?
Height is the y value. So if you look at this picture here, at any given point, to see that the height is the y value, how tall the curve is at any given point. So can you imagine I try to find the average height of this function by doing an infinite number of points and finding out what the value is? And
Mhm.
if you did an infinite number of points, wouldn't that basically be the area?
Mhm.
And
I
then you
was just-
divide it by b minus a.
Yeah, I was just a little bit confused because on the section on like the shells, it was the
Yes.
height was like horizontal. I was confused about.
Yeah, the word height was being used in a different context there.
Oh, okay.
I guess I could have called it the length of the rectangle. That might have made more sense. But sometimes when the rectangle is vertical, it is a height, and sometimes it's horizontal. I guess you should call it the length if I was being more precise. I just want to check this guy out since I said that, and I hope I haven't screwed up. Then I should be able to put in 3 times, put a bracket around it for safety, cosine x cubed, followed by a sine x. And I'll go to the window and do a 0 to pi. And I'll do a zoom to fit. And what I want to see is the shape above and then the shape below. Does that match what I said would happen? Can you see that the top bit and the bottom bit are exactly the same, but one's plus and one's negative? Actually, I'm not sure it's worth it. But couldn't you just plug every function in case that happens, in which case you can just go straight to the answer and put 0 in and save maybe 5 minutes of working? But I'm not sure it's worth it, to do it that way. This is nicer, right? This is just cool math. Cool math is always going to be nicer, in my opinion. Okay. Let's see where we can go next. Right. Well, imagine this is our next. Oh, darn it, time's beating me. I'll talk about it and then tomorrow we'll do some. Imagine you've got your starts here at A, does its thing, finishes up here at B, right? Of your classic function. And you've found the average value, and it happens to be, say, here. Let's just pretend it is anyway, right? Okay. Wouldn't it be nice to find a number called C that had the property that the value of the function at C was the same number as the average value of the function? The logic goes something like this. If a curve starts here and it's continuous and it finishes here, and it has an average value, then shouldn't there be at least one place, at least one, there might be 2 or 3, right? Where the curve will have the same, there'll be a place on the curve that has the same value as the average. Does that make sense? And so what you're going to do is you're going to find the average value. And then you're going to try and find a number, a C, on the curve that has a function at C equal to that average value. So let's do a really quick one. Let's suppose I want to find the average value of x squared between 1 and 2. If I sketch x squared, it looks like this, but between 1 and 2, it looks like that, right? So its average value is 1 over 2 take away 1. The integral from 1 to 2 of x squared dx. That's nice, that's just a 1. That's going to be 1/3 x cubed. 8/3 take away 1/3. The answer, I know it's really fast, isn't the average value of this function 7/3. So can you imagine somewhere around about here, right? You get 7/3. Our last piece of the puzzle is to find the x coordinate, right? The C value that has this property. So what am I trying to do is I'm trying to solve when is the function equal to its average value. So when is the function, which is x squared, equal to its average value, 7/3? In this case, won't the x coordinate just be the square root of 7/3? Which I guess I could try and make pretty, but really I'm not going to do a good job of it, right? So an x value of square root of 7/3, that's essentially where that is. There is at least one point in the curve where the function has the same value as its average. What would the logic of that be? Suppose today, starting at midnight and finishing at 1 second before midnight, suppose today the average temperature was 51.21 degrees, right? 52.21 degrees. Isn't there guaranteed to be at least one point today where that is the temperature? Right. It might start at 45, it might go up to 60 and then drop down to 40. But somewhere in that big curve, isn't there at least one point in the day, and there might be 2 or 3 points in the day, where you hit the average value for that day? And that's an important number to know. It kind of tells us a little bit about what's happening. Whether it happens early on or late on gives you an idea of how steep the curve is, for instance, things like that. And that is us, at least for today. Any questions? Okay, I'm going to hang around in case any of you may have some. Oh God, what a memory. Will you say hi for attendance? And while you're doing that, I'll say, I'm going to hang around at the end. If anybody's got some other questions, homework for instance or whatever, I'll try and fix them for you. And if not, that's great too.
Professor,
Yes.
I was wondering because I don't have Wi-Fi right now.
Right.
And do you think I can do the homework on my phone? Do you think I'll be able to do that?
Yeah, you could try if it's a good enough phone. All you really need is to be able to see the picture. So I've never tried to do it on a phone. Can you do that little spready finger thing and it zooms in enough at least for you to read the questions?
Yeah, I think it'll probably be able to do that.
Right, and you'll do most of your working on paper, so that won't affect the power situation. And then most of the time, isn't the answer just 5 plus root 2? And so you don't actually normally write a lot. So try it out. If you have any issues, you can tell me about it.
Okay, thanks.
You're welcome. Right, well, hi Douglas, so you got a homework question? Is that why you're in?
Yeah. So
Okay.
I have a few problems left. I'm having a little hard time understanding when to subtract. I understand how to find the height and radius because the radius is from the axis of rotation to the curve, and then the height is the perpendicular to the radius.
Okay, it depends on if you're rotating about the x and y, but yes.
Yeah. And yeah, so could we, I know you talked about it, about when you're supposed to subtract the number to x first, and you said it was from the left to right? Or,
yes.
Okay.
Yeah. Do you want me to talk about that a little bit?
Yes, please.
Okay, so I'm going to zoom over to my screen situation. Here we go. So let's suppose we're rotating about the x-axis. Let's just keep it as the x-axis right now. So what you've got is you've got your curve. There are two methods each one distinctly different. And so what you do with one method is not the same as what you do in the other method. So that's important. So do you want me to talk about the disk first and then the shell second?
Yeah.
Okay, so imagine that we have a curve and it goes something like this. Call it y equals f of x. And I'm going to do a disk method. And so I've got my shape and it goes something like this, goes something like this. And in this particular situation, what you have to imagine, do my green thing, is your rectangle will look something like this. And if you imagine that point there as being x comma y, right, then you talk about this as being position x, right? And this here is position y, right? So we need to know in this question who the radius is and who the height is. So this is the simplest situation. Because we're on the x-axis, at least, it's the simplest situation. So we need to know radius and we need to know height. So when we do it in this particular combination, the formula doesn't have a height because the formula just has pi radius squared, right? So what is the radius? The radius is the distance from here to here. So the radius is the distance that is.
So that would be the function, right?
So that would be the function. So in that situation, the formula looks like that. Now let's take that same picture and rotate it about a line like y equals 3. Now we still have the same start and finish. We have the same rectangle, but the formula for the volume is now going to be what we call pi big radius squared take away small radius squared. In this case, that distance from there to there is the small radius. And this distance from here to here is going to be the big radius. You can imagine that point there, right? From here to here being the y value. Y equals f of x. So the big radius is that bit plus a y. So the big radius, right over here, is going to be that distance plus this distance. So that's going to be a 3 plus a y, and that's going to become 3 plus f of x. So whatever f of x is, 3 plus f of x is the big radius. Now, what will the small radius be in this situation?
3.
And it's just a number, right? And that takes care of that situation. Now let's do the ultimate version of this, where we have y equals f of x. We have another one up here, calling it y equals, g of x. And it's going to start here. It's going to finish here. And we are going to rotate it down here at y equals 3 again. Let's see what happens to our rectangle this time. Well, based on distances, the short distance, there to there, is small radius, and the big one is that one. So my volume is going to be the integral from A to B of pi, the big radius squared, subtract the small radius squared, dx. This big one and this small one go different heights. One reaches the height g of x, the second one reaches the height of f of x. Right? So when I'm looking at what these are equal to, the big one, which is here to here, is made up of two pieces. It's made up of this distance, which is 3, plus the height. So this is going to be 3 plus g of x. The small one is very similar. It's made up of this bit plus the height. And this is 3 plus f of x. So if you go in here, you're going to do the big one, in this case, that one happens to be. And g of x are just placeholders for whatever function happens to go there. Now, each of these two guys, I have put the axis of rotation parallel to the x, but I've put it below the guy. So what's going to happen if I take that same picture, there's my y equals f of x, there's my y equals g of x, and I start here and I finish here, but I rotate about a line that's way up here. That's the shortest one of the two. That's the small radius. And this one, that's the large radius. So as long as I can find out who these two guys are, I've pretty much done the question. So let's find out how you find the small and the large, or the big. Keep switching between word big and large and so on, but it's the same word, same thing. Right. How are you going to get that distance? Well, if you wanted to only find this distance from here to here, couldn't you find the total distance from here to here, which is 10, and then take away the height of the function? So won't this distance be 10? Take away this piece, g of x. Do you see how it's now not add, but take away? And if you want to get the other fella, so once you've figured out what one is, you'll quite soon realize that whatever you do to get the one, you do the same thing to get the other. And so whatever f and g are, these are the guys I will use in big and small and squared and so on and so forth. So what we've kind of covered here are all the permutations of one or two curves, x-axis or parallel to the x-axis situation. So there are lots of combinations out there, I guess. Single function x, double function x. Single function parallel to x, double function parallel to x. Have the line below the x-axis, have the line above the x-axis. You see all the different permutations, but they all boil down to finding these two things. What's the biggest distance to the axis of rotation, and what's the shortest distance, and making sure that they're in terms of x. So how do you do y? Can you just imagine the shape's turned on its side? Can you see then that the furthest one is going to be your big and the shorter one is going to be your small? So the one that's furthest to the right, isn't that going to be your big, and the one that's not is going to be your small. So if you draw a picture of the thing, you can visualize the up and down ones, which we have covered. But if you imagine everything just doing a little 90-degree turn, isn't it all about left and right? And when you measure the distance, you'll be finding f of y and g of y, right? Because it'll be in terms of y when you go horizontal, right?
So is it going to be the same for the shell method too?
No, in the shell method, all bets are off. In fact, it's best not even thinking about the shell, the disk method when you're doing the shell method. Just don't even think about them. They hurt your thought process rather than help it. Now, let's show you what that fella looks like. The only thing that really makes them similar looking is that, what am I rotating this about? Okay. Is that you take some area and you rotate it about an axis. So that's the similar part. But the way you go about it is quite significantly different. So let's suppose I wanted to rotate something about the y-axis. Now, if I'm doing the disk method, if I rotate something about the y-axis, don't you do everything in terms of y, right? It'll be distance, big guy squared, take away little guy squared, dy. But in the shell method, it's the integral from a to b of 2 pi radius height dx. So how do you find those guys? Well, you build a rectangle. Here's the first difference. Do you notice that the rectangle is parallel to the axis of rotation? When we did the disk method, do you notice that the rectangle was at right angles? Right, it was perpendicular to it. So even the way you draw your rectangles are different in the shell method. Y-axis, vertical. Y-axis, axis. That's different. Pretty much everything is different. Right, now, the guy we call height, is that different? That guy there. In this particular question, isn't the height just the value of the function? The distance from there to there is the y value. Now, the radius is the distance from the rectangle to the axis of rotation. Now, if you imagine that point as being x comma y, won't this distance be y and that distance there be x? So the radius is x. And you end up with the integral from 0 to pi, 2 pi x, f of x, dx. So provided you're rotating about the y-axis and it's a single function, that's the formula that will get you the volume. So a single curve being rotated about the y-axis, this is the formula that will get you. Right. Now, if you start moving things around, then all bets are off. Let's suppose I take the same function. But I decide to rotate it about this line over here, which is what x equals -3. If I put my little random rectangle that distance there is X, this height here is Y. Good. Let's see what we get now. The radius is that distance there. The height is that guy. So the volume is going to be the integral from A to B of 2 pi radius height dx. Now, that position there is x. What do I mean by x? I mean that distance there, right? Is x.
Would you add 3?
Yes.
Because that's how much farther away it is from the x-axis.
You would do exactly that.
And then the y is just the function.
Yeah.
Okay.
Begin to click.
Yeah, I think so. Could you do like a really quick example of a subtraction one? Because that's the ones I'm having a hard time with. Is it just like?
Yeah, yeah. The subtraction one is really just a matter of where the axis of rotation is. So. Let's have it way over here at x equals 20, right? Here's my little rectangle. That distance is x, right? This distance is y. The radius is the distance from the rectangle to the axis of rotation. Okay, now, the total distance from the y-axis to this line is 20, right? That total distance from here to here is 20. The distance from here to the rectangle is x. The piece that we want is the other bit, right? Which we're calling the radius. Can you see that 20 take away x is that guy? And so when you do your integral from A to B, 2 pi radius height dx, you're really just going to go and do, oh, I forgot to write that down. The radius would be 20 take away x. And won't the height just be the value of the function? Now, what I haven't done, but actually it's very easy to do here, is do you imagine it wasn't just f of x, but another piece here going g of x? So there's two curves. Do you know the nice thing is that they're dead easy to cope with. See if it's a top curve and a bottom curve like this, f of x, g of x, isn't the height just f of x take away g of x?
Yeah.
And so you just change that to an f of x take away g of x, and that takes care of that. Now, if you do everything the other way around, don't you just do the same job, but now everything's y's instead of x's? So it's x equals y cubes, and x equals f of y. But the process is really just.
But you're still trying to find the radius and the.
Yeah, you're still trying to find the radius and the height.
It's all the same. Okay.
All
great.
the same.
Thank you.
You are welcome. Are we good, Trenton? Have you any questions?
I'm all good. Yeah.
Okay, then if that's it, I'll call it a day and I'll see you tomorrow.
Thank you.
You're welcome.
Thanks.
Oh, guys, do you mind if I actually take this bit of the video and stick it somewhere so others can see it?
For sure.
Yeah. Sure.
Okay, thank you. I might just tag it on actually at the end of this video. It's probably easiest. Okay, right. Well, thank you again. Bye-bye.